So today we are going to discuss on how to implement a very simple functional coverage for a very simple design. So first, let's begin with the basics. So functional coverage is explicit in nature, so which basically means that it is implemented manually by the user, and the user should have some knowledge of the architecture, and the design specs. So using those information, we will have a verification plan, and inside the verification plan, there will be several test cases, which ranges from critical to some not so critical ones. And using those test cases, we will implement functional coverage. So for now, for the sake of this example, let's begin with a very simple design. So for this example, I will just design a very simple buffer. So I will add a new file. It should be of .sv extension, and I will name it buff. So it will have an output y and an input a. So both the output and input will be of 4 bits. And also I will name the module as buff. So I will begin with my top level test module. So first I will mention the name of the module, test, and then I will mention the signals. And then I will instantiate the DUT. Also, I will include the design file. So after doing the instantiation, I will begin with the format of functional coverage. So first of all, to implement functional coverage for any design, you need to mention a cover group. So a cover group is a user-defined construct that comprises or encapsulates the functional coverage model specification. So it has lots of things. It has the signals for which you will report the coverage. So it includes cover points, beans, etc. So first I will begin with the format of the cover group. It is just cover group, and then you have to name the cover group. For my example, I am naming it cover underscore a underscore y, and then it is followed by a semicolon, and then you have to just end the cover group by writing end group. So it is very similar to other system Verilog constructs like task and function, where you have to just write function, then at the end you have to write end function. So after that, inside the cover group, you can write many things. So first of all, I will begin with a cover point. So cover point are the expression to be covered under cover group. So cover group basically points out to the signal. There are two signals. So it points out to the signal for which you need the coverage. So the format is very simple. So first I will write the optional label, which is optional. So label is written like this, and it can be avoided. After that, you have to write the keyword cover point, then followed by the signal you are aiming to report the functional coverage for. So let's focus on the signal A. So what this will do, it will just basically cover all the, it will look for all the possible values of A, and it will check whether all the possible values of A are covered or not. So since A is of 4 bits, their possible values ranges from 0 to 15. So it will look whether when you apply the stimulus, and it will check whether all the possible values are covered or not. So now just to make this cover group works, you have to mention the object of this cover group. So just like any other class, you have to declare a handle, and then you have to use the new constructor to assign an object to that handle. So the name of the cover group is cover AY. So I will write it. And after that, you have to mention the handle. So for this example, I'm writing the handle as CAY. Then you have to assign an object. So the entire cover group has been implemented for this design. Now you have to find a way to apply stimulus to check for coverage. And for that, I will begin with my initial block. And inside the initial block, I will just write a for loop which ranges from 0 to 15, and it will cover all the possible values for the variable A. So I will just assign all the possible values to A, and in the next time slot, I will write a checker using the if condition, which will just check whether the value of y equals to A or not. And if it is not, then it will display a small message. Okay, it is supposed to be y. And there is also one last thing that I need to do is to sample the coverage value after every change is made. So there are two ways to do that thing. The first one is to do the automatic sampling by using the @ keyword and writing a sensitivity list. And inside the sensitivity list, you have to mention the signals during which you want to sample the values or the coverage. And the other way is a manual sample, which could be done just by writing the object or the handle of the cover group dot sample. So for my first simulation run, I am doing the manual sample, and let's find out whether it works correctly or not. So remember, it is important to give a delay of one time instance because the output needs some time to get the response from the DUT. So I will save the code, and first I will check for any compilation error. Okay, it's fine. So I will go ahead and run the simulation. Okay, I made a typo, I think. All right. Yeah, it is supposed to be buff. Also, I forgot to write the combination logic inside my design, and since it is a very simple buffer, I will just use continuous assignment to assign the output y with the input a. Now I will go ahead and I will run the simulation. So our simulation has begun. So to get the coverage report for our functional coverage inside QuestaSim, there's a command that you have to write right after the simulation check. And that command is coverage report. And that will show that whether we get 100% coverage or not. As you can see right here, that it says 16 beans have been created and all of them are covered. It is because of the fact that we write a cover point for the signal A, and since signal A is of 4 bits, so there are 2 to the power 4 multiple or possible values, and for those possible values there are a single bean which have been created. So that bean will track that how many times that value have been hit. So right here, as you can see, we have been providing stimulus, and since I am using a for loop for only one time and the range of the for loop is from 0 to 15, each of the bean which have been created right here implicitly have been hit for a single time. So there is another coverage keyword which will show everything in more details. So it is very similar to that thing. You have to write coverage report, and you have to add one more argument that is followed by hyphen detail. So that will show the progress or the hits of every beans in detail. So as you can see that there have been 16 beans created, and all of these beans are mentioned to be auto. So we haven't mentioned any beans explicitly because we just wrote cover point A. So here all the beans have been implicitly created, and this detailed coverage report show that for how many times these beans are hit. So as per our stimulus, each of this signal are hit for one time, as you can see right here. So this is the default coverage goal, which is 100%. And as you can see it right here that our metric is 100%. So we are getting 100% functional coverage. And this section shows the total number of beans. So there are 16 beans and all of those are covered. So you can see it right here that our goal hit number was 1 and the 0th auto bin has been hit for one time. And same goes for the other bins. So what happens if we write another for loop? It will just get multiple hits. So let's find out. I will quit the simulation and I will copy this for loop and I will paste it. And this time I will remove the manual sampling and I will just use the auto sampling. And to do that, you just have to go to your coverage signature, and here you just have to write @ and you have to mention a sensitivity list like the always block. And when it detects any change on the signals which are mentioned inside the sensitivity list, the coverage will get sampled. So here I will mention A, and there are 2 for loops. So we will have multiple hits for each of the automatic beans. So let's go ahead and save the code and run the simulation again. Now let's print the coverage report in details. So as you can observe right here that our coverage goal was already made with just a single hit, but here we are getting 2 hits for each of the beans, and it is because we are providing the same stimulus again using the another for loop. So this is the coverage report in detail, and now I will show you a way to implement explicit beans. So each of the beans were implemented implicitly because you didn't mention any beans. You just used the cover point keyword and it automatically inferred all the beans. But you can also explicitly mention the beans, and each beans will have they can have a single value or even a set of values. So let's go ahead and implement explicit beans for our signal Y. So I will quit the simulation right here. I will delete this for loop. So I will mention another cover point and I will give the label CP2. And this time, since I'm writing the cover point for the signal Y, I will write the keyword cover point followed by the signal itself. But this time, if you want to mention the beans explicitly, you don't have to write the semicolon. Instead, you will write the beans inside the curly brackets. So I will write the curly brackets, and inside this, I will mention the beans. So you can mention the beans by using the beans keyword followed by the name of the beans, and name of the beans are user defined. You can name it whatever you want. So for my first bean, I will write it B1, and then after that you have to assign some values to those beans. And you can just do that simply by writing the curly brackets again. So this syntax is kind of very similar to C. So after every beans, make it sure that you're writing a semicolon like this. So you can keep on writing another beans after this, followed by semicolons. So inside the beans, you can do a lot of things. So for the first beans, I'm giving some random values. Let's give it 1 and 10 and 13. So here, what will happen? So y gets whenever y gets any three of these values, it will detect a hit. So this will create a single bean, unlike the automatically inferred auto beans, which are right here. So if you do not mention anything explicitly, it will just create automatic number of beans, which depends that what is the how many values that particular variable can support. So here I have mentioned only one bean explicitly. So this cover point will only focus for the signal y when it gets either three of these values. So since we are exercising all the values ranging from 0 to 16, this cover point should get 3 hits. So let's find out. And remember, it should have only one bin. And this bin is not automatic since it is explicitly mentioned. So I will go ahead and, oh yeah, one more thing. I will also mention the signal Y in the sensitivity list. So whenever there is any change detected on either of these signals, the coverage or the cover points will be sampled. So let's go ahead and simulate the code. Okay, for some reason I mentioned the same label, so the label should be different. So I will go ahead and run my coverage report. So as you can see right here that it is same for the cover point CP1 that there are 16 automatic beans, but for the cover point CP2 there is only a single bean. because it has been mentioned explicitly. And you can see it right here that the coverage goals have been met and there are 3 hits. So it has basically only one bean and it detects a hit whenever it gets any of 3 of these values. Since we are providing the stimulus of the values ranging from 0 to 16, so all of these 3 values were covered and it detects a total number of 3 hits. So using this, we can mention a lots of beans. So let's go ahead and mention other beans. So for the other bean, I will name it B2, and you can just explicitly mention a value and you can also mention a range. So let's say I want this bean to cover a range of 1 to 2. Since our stimulus is providing all the possible values, this particular bean should get a total number of 2 hits. So let's go ahead and run the code. Let's go ahead and print the coverage report. So as you can see right here that our second explicit bean is getting a total number of 2 hits, which is quite evident right here because we are covering a range which ranges from 1 to 2 and all of these values are covered. So similar to range, we can do lots of other stuff. So I can also write beans B3, and what if I write a an empty square bracket? So if you write an empty square bracket and you give it some values, let's say let's give it 2, 6, and 11. So what it will do, it will automatically create a number of different beans. So whenever you mention empty square bracket after the name of your bean and give it some values, so depending upon the number of values, it will create automatic beans. Not automatic beans, different number of beans. So since we are giving 3 different values, this should have 3 different beans. And each of the beans will have this single value. So there will be a bean called B3 0 and it will have a value of 2. And there will be a bean called B3 1 and it will have a value of 6 and so on. So let's go ahead and run the simulation. So as you can observe right here, that using the empty square bracket, this bean created three different beans, and each three of those covered these values. So you can see it right here that each three of them are getting a single hit. And it also mentions the value it is covering. The naming convention is done as per the value which is getting covered. So the bean B3 2 is covering the value of 2, the bean B3 6 is covering the value of 6, and bean B3 11 is covering the value of 11. So what happens if you use the empty square bracket with some range of values rather than some values? Let's find out. So I will mention another bean, and this time I will mention some range of value. So let's give it from 0 to 8. So what it will do, even though it has a range of value, it will just divide. It will just divide these ranges and it will create a separate bean for each of the values in the range. So there will be a separate bean for the value of 0 and a separate bean for the value of 1 and so on. So it also works with the range. So let's go ahead and run the simulation. So as you can see it right here, that bin B4 has created 9 different beans, and each of them are covering values ranging from 0 to 8. And each of them are getting a single hit. So, I mean, this is the advantage of using an empty square bracket and assigning it with some range or even some direct values. So, there are a few more things that you can do with the beans. So, you can also mention some value inside the square bracket. So, let's do it. So, I will name it B5. This time, I will write some value inside the square bracket. So right now I'm writing 4 and I am assigning it to the very same range of 0 to 8. So what this basically does is that it limits the number of beans that can be created for the range of value or for whatever values you are assigning to that particular bean. So right now I have mentioned here 4. So there will be 4 beans 5, and the range of values will be divided amongst those 4 beans. But observe, we have a total number of 9 elements, which is odd, not even. So how the division will work? So it will work like that, that the first two values that are 0 and 1 will be assigned with B5. So the first two values will be assigned to the first bean, and to the second bean the next two values will be assigned, And with the third bean, the next two values will be assigned. Then with the last bean, the remaining values, which will be 3, and those values will be 6, 7, 8. So those of the values will be assigned with the last bean, and that bean is going to be bin B5 3. So let's find out whether it is true or not. I will save the code and I will run the simulation. So as you can see right here, that by mentioning some value inside the square bracket, it limits the number of bins that can be created, even though if there are more number of elements assigned to it. So even inside this particular range, there are total number of 9 elements. Each of the 9 elements are divided. So the first element of the bin B5 gets a total number of 2 hits, which basically means the value of 0 and 1 is covered right here, and the value of 2 and 3 is covered right here. The value of 4 and 5 is covered right here. And finally, the remaining values, those are 6, 7, 8, is covered right here. So that's why it is showing our total number of 3 hits. So that's basically all the possible and basic things you can do with the beans keyword. And there are lots of things that I need to cover. And also I need to mention one final thing. You can also write a bin which will have a start point. So it will be a single bin. And suppose if you want to cover a range of value and you want to start from some point, let's say 4 in this case, and you just want to cover all the values, all the possible values till the end. So if I want to cover all the possible values from 4 till the end, and the end here is 15, I can also write the dollar. And dollar basically means that all the values from 4 till 15 will be covered with this bin. So let's go ahead and run our final simulation. Okay, I did make a mistake. Oh yeah, since it is a range, it should be inside a square bracket. Now it should work fine. All right. Okay, it was a typo. So as you can see it right here that it covered all the values that are ranging from 4 to 15. So there are total number of 12 values. So it gets the coverage for those 12 values and or hits for those 12 values. So these are some of the basic stuff you can do using the beans keyword, and you can mention the beans explicitly. So remember, if you do not mention anything and you just write a semicolon, the beans will be inferred automatically, which is the case right here. And it depends on the total number of possible values that that signal can have. And there is also a limit for that. And by default, that limit is 64. So there can be 64 automatic beans, and which can be changed. So there's a method to change that, which I will cover in my upcoming lectures. So right now, just remember that if you do not mention anything, the beans will be created implicitly. And if you decide to write beans explicitly, so only those specific number of beans will be created, and as per the values assigned to those beans, the coverage will be sampled, which you can see right here. And remember, just do not forget the sampling. So here I did the automatic sampling as per the sensitivity list. And you can also mention the sampling keyword manually using the handle.sample. So also the other thing is obvious that like class, you should also create an object for the cover group. Otherwise, the command of the QuestaSim, which is coverage report, will not detect any coverage or any functional coverage. So I hope you find this video useful and stay tuned for more. Thank you so much.